Over the centuries, the low-lying Netherlands has endured a series of disastrous floods. Each one has made the Dutch realize anew that for them, life and death are separated only by the width of a dike. The 1953 disaster drove this lesson home yet again and provided the impetus for a vast new scheme. Named the Delta Plan, it was worked out by a group of experts and passed into law by Parliament.
De uitslag van de stemming is dat 106 leden zich hebben verklaard voor het wetsontwerp en 8 tegen, zodat het is aangenomen.
The primary aim of the Delta Plan is to secure more safety for the whole of the Netherlands, for which the existing dikes and sea walls will be heightened and reinforced. The main project lies in the southwest of the Netherlands, where the coastline will be shortened by 700 kilometers by siting 4 large dams in the Haringvliet, the Brouwershavensegracht, the Oost-Teschelde, and the Viersegracht. East of the islands, 3 smaller dams will be built, which provide the means for a better control of the sweet water supply in the center and northern regions of the Netherlands. Arterial roads built over the dams will help to open up this very isolated area. The dikes, too, will create a barrier behind which the delta waters will gradually become sweet, important for agriculture and cattle breeding. All great hydraulic schemes have their own specific problems, and the Delta Plan is no exception. For one thing, enormous masses of fast-flowing water produce large areas of shifting sea bottom on which one cannot build a dike. Dutch dike builders coped with similar problems for centuries by covering the bottom with reed and osier matting. Weighed down by stone, each mat and stone is made and placed by hand. These methods are not only time and labor wasting, but now require impossible amounts of stone and willow. Building up the body of a dike has been mechanized in the past decades, but it still takes too much time. Dike revetment used to be an ingenious handicraft, and the result was fine and strong, but time-consuming and therefore costly. The general technical developments of the past few years and the universal increase in mechanization are also reflected in hydraulic engineering techniques. In place of willow, nylon is used. Nylon mattresses, weighted by sand, are laid by a specially designed machine. Folded like concertinas, they lie on the platform of this vessel, which is conveyed to its location by crane. The vessel is lowered to the seabed, and as it moves forward, the folded nylon mattresses run off the front to lie underneath. So flexible is its construction that it readily conforms to the undulations of the seabed. The nylon, too, fits snugly. Thus, this machine takes over the job of numbers of laborers. As for the laying of stones, which is still occasionally necessary, even when nylon mattresses are used, mechanization has replaced the classic craft. Today, the job is done by tilt bins, hoppers, and tipping buckets. Mechanization, too, in building the body of the dike. Suction dredgers, drag lines, and bulldozers complete in a few hours work which previously took a complete army of laborers several weeks. The rapid mechanized construction of the body of the dike must be followed by a rapid finish. A machine-laid sand bitumen revetment was the answer. In the past, hydraulic engineers bossed hundreds of laborers. Today they direct suction dredgers with or without floating lines, stone cranes, drag lines, bulldozers, and finally, the latest defense against fast-flowing water, the caisson. Caissons were introduced into hydraulic engineering for the first time in 1945 with the reclamation of Walcheren. The proper use of caissons demands a good deal of preparatory work. Problems studied in the hydraulic engineering laboratory at Delft included current flow and the forces it would exert on cables. Once these questions were answered, the entire organization of the operations were rehearsed beforehand around a dry model in which the water is simulated by glass. Here, every member of the team is given his job and briefed on the part he'll play in the scheme. Since World War II, invaluable experience with large caissons has been gained in various operations, among them being the reclamation of Walcheren in 1945, the damming of the Brachman in 1950, the Brielse Maas in 1952, and the reconstruction of the dikes in 1953. Now, a part of the Delta plan, the three islands. South of Rotterdam lies Hellevoetsluis, a little town on the Haring Fleet. Once an important naval harbour, it had been in slow decline for centuries. Now it's come back to life with the army of Delta navvies billeted there. In the middle of the river, virtually in the open sea, a complex of sluices and locks is planned. To enable these sluices to be built, it was first necessary to create a ring dike or cofferdam in the middle of the Haring Fleet. Once done, the centre was excavated to make foundations on which the sluices are now being built, at a depth even lower than the original bottom of the Haring Fleet. The actual construction was, of course, preceded by careful surveying, for which a number of towers were built. Then came the floating grabs to build the clay banks. Here is the first tiny island, which will ultimately grow into the enclosing wall of the cofferdam. The cofferdam was built on two sides simultaneously. After 7 months of dredging, pressing and sand pumping, the ring was sufficiently advanced to be closed. Closing the last gap in the ring, bulldozers, cranes and sand dredgers are concentrated in force, for the gap must be sealed before the tide turns. This is the completed cofferdam. It measures 1/2 by 1.5 kilometers, costs 20 million guilders, and will cost another 10 million to clear away again once the sluices are ready. Here you see a model of the dike and 3 of the drainage sluices. The sluices serve to control the waters of the Rhine and the Meuse, and in severe winters for the removal of ice. In contrast to the works in the Vissershaven, the emphasis here is on the sluices, for when the dike is closed they perform the same function as the open floating caissons, that is, to allow free flow to the tidal stream. Intensive pile driving goes on in the pit. A start has been made on pouring concrete for the floor of the sluice. On this floor are to rest 16 pillars connected to each other by a concrete triangular bridge. The floodgates will be hinged on the bridge, and over the bridge will run the arterial road connecting Rotterdam with Flushing. 1,000 pumps are lowered deep down to keep the 17-meter pit dry for 4 years. An electricity generating station, large enough to supply a medium-sized town with light, provides the current to power the pumps. Piles, 24 meters long and each weighing 7,200 kilos, constitute the foundation for the floors of the sluice. Pile drivers work for 2 whole years to drive piles and sheet piling into the ground. Headhunters is the slang term for these men. Their job is to strip the heads of the piles so as to secure the reinforcing metal to the floor or pillar which it will have to support. A network of braided reinforcing steel is made to form the backbone of the concrete works. These rods are as thick as a man's wrist. Once the network for one base section is complete, it's covered with concrete, which is produced on site. Hour in, hour out, for 48 hours the big trucks lumber over the Bailey Bridge to dump the concrete. For each base section, 4,000 cubic meters of concrete is used, or about as much as is needed for 10 medium-sized houses. This part of the scheme will go on for 8 years, with a task force of 800 men and consuming 500,000 cubic meters of concrete. More figures: 25 million kilos of steel, 38 million kilos of reinforcing metal, 22,000 piles. When completed, this sluice will have 17 openings, 34 gates, and 68 engine rooms. From 1968 onwards, and for the first time in history, the tides of the hiring fleet will have been tamed.